of a wave sitting on the tropopause, just like I showed in the animation. Stratosphere is shaded, and here's troposphere. So assume that this is like that isentropic surface that I showed. Here's your tropopause, and I put a wave signal on that tropopause. Now assume that that wave signal on that tropopause grows in time. So what's going to happen is I'm going to go from this envelope to the dashed line over here. This is my wave growth, right? And in order for that to happen, I need to have positive v prime over here to move it that way. But when I do that, I'm moving smaller PV poleward, which is a negative q prime. And then over here, I do the exact opposite. I move positive q prime equatorward. So I have negative v prime coupled to positive q prime. Okay? So if I put these two things together, I get them anti-correlated, and I get a negative PV flux during the wave growth. Just from the fact that the wave is growing, I'm fluxing PV down gradient. If I now reverse this whole scenario, I go back from this dashed line, which is now this envelope here. I go back to the initial wave. I'm fluxing everything back to where it came from, so I have to have the exact opposite fluxes in this case. And surely enough, what I'm doing is I'm taking negative q prime here, and I'm fluxing it back equatorward. And here I'm taking positive q prime, and I'm fluxing it back poleward, and I get a positive PV flux. So in the transient situation, I can actually get positive PV fluxes, but it's only because I'm looking at the wave decay stage. And really, I need to look at both the wave growth and the decay. And if this is all reversible, as I've drawn it in this case, I average in time, and I get 0 PV flux. Okay? So if all I have is a wave growing and decaying, I have no net PV flux from that. What needs to happen is something irreversible, like a wave breaking kind of situation, which I've showed in the animation before. We have overturning contours of PV. So what happens in this case, say you have this overturning contour like that. In order to get here, you had to have those negative PV fluxes in the wave growth stage. So they are already there. But what's going to happen is this part over here has a reverse PV gradient, and it's going to be cut off from this and then going to be mixed into the surroundings. So when I go from this stage into the wave decay, I have less PV to flux back than I had to flux forward initially, which means that the up gradient fluxes in this decay stage are going to be smaller than the down gradient fluxes before. And if I now time average, I have a net negative PV flux. So the wave breaking gives me my down gradient PV flux. So it's really a signature of the waves breaking. Okay? And just to make really sure, the only way I had upgrading fluxes is in this wave decay stage there. So now let's move to actual data and look at how the PV fluxes look like. In order to do so, I need to go from my quasi-geostrophic framework, which is a little easier to discuss here on the slide. I need to go to a framework, an isentropic or potential temperature coordinates. And I've written it all down. This is the definition of PV in this framework. This looks like the shallow water PV equation with the thickness here, very similar to the oceanic context where you'd have the buoyancy gradient there, or the density gradient. And this is my Enstrophy budget. It just looks a little bit different, but it's really the same as before. And I'm going to use reanalysis data for the atmosphere from eSIMWF to analyze this. And I've computed all these terms. And at first, we're going to concentrate on this production term, right? And so remember, the prediction is that this has to be down gradient so that the PV flux multiplied on the background PV gradient should be negative everywhere. So here's the climatology of this field. So this is PV flux times the background meridional gradient of the PV. Use the QG version of it. And December, January, February is on the right, and June, July, August, southern hemisphere is on the left. Sure enough, this is mostly blue. That should be the first thing for you to see. This is mostly blue, and blue, it means negative values. So for the most part, I really have just down gradient eddy fluxes of potential vorticity. Here's along the tropopause in mid-latitudes. I have a lot of wave activity there, a lot of down gradient fluxes. This is up in the stratosphere. I have a lot of stuff going on there. But then there's this interesting feature right here at the subtropical jet, where the PV fluxes are going in the opposite way from what they should do based on our prediction. They're positive there, right here. And not just are they positive there, they're positive, they're up gradient in a region where the background PV gradient is very strong. So it's not that you got the up gradient fluxes in a region where the background gradients are small and so maybe it can happen, that kind of thing. They exist in a region where the background gradients are very strong and positive. So you have these up gradient fluxes there. So what's going on with that? So that's going to be sort of the rest of the talk. So first of all, here I showed the PV flux multiplied on the background gradient, so you can really see whether they're down gradient or up gradient. But you can take that background gradient out of it and just look at the PV flux. Remember, this is the eddy forcing on the zonal mean zonal flow. And you still get that positive flux there. And so there is an actual positive forcing on the mean flow here. I'm going to illustrate that a little bit further later on. Here's your big negative PV fluxes. And just to make sure, down at the surface, you actually have positive PV fluxes, but they're not down gradient. Rather, the PV background gradient is reversed near the surface, where you have instability, generation of eddy activity. And so those positive PV fluxes here, they're actually still down gradient because the background PV gradient is reversed. Okay. So this is the PV flux, and to make sure, this is very different from what you would get from a passive tracer. Just to make sure you can see that this is just I grabbed one. This is ozone fluxes from the same data set, and the black contours show you the meridional gradient of ozone, which is positive everywhere here, and you see that everything is blue, everything is negative in this case. So the ozone fluxes are down gradient everywhere, and you don't see this little spot there with the positive PV fluxes. So there's really something going on here to PV where it does not behave like a passive tracer. It doesn't behave like a chemical tracer. It behaves like a dynamically active tracer there, and I'm going to get more into that. There's a funny little region here where the ozone fluxes are the other way around, but the background gradient is also the other way around, so they're still down gradient. Okay. So just to make sure you understand what's going on to the mean flow tendency here, this is a line plot across latitude of the mean flow tendency coming from these PV fluxes on 350 Kelvin, so approximately 200 hectopascals. So you have negative fluxes, and then here you have those positive fluxes, the up gradient fluxes. So down here, the black line shows you the subtropical jet profile, basically, right? So you have your core of the jet there at 30 degrees latitude. And all I've done is I've just ad hoc taken these tendencies and I've applied them to the black line there over several days, just to show you what would happen if this was all that there was happening. And as you apply this over time, what happens is that, well, they're slightly poleward of the jet maximum. So what you do is you shift the jet poleward, but at the same time that you're doing that, you're also sharpening the jet. The final result after 10 days here is a much sharper and poleward shifted jet. So there's a really important tendency that's coming from these positive PV fluxes. I'll skip that. Here's a seasonal evolution. This is the northern hemisphere, just to show you that this is not something that just, is there at one time. Throughout the cold season in the northern hemisphere, you have these positive PV fluxes right there, close to the subtropical jet core, which is marked here. And they're sort of all the time acting to pull the jet poleward. And the same thing happens in the southern hemisphere in that cold season, that they're at the flank of the jet and they're at all times trying to pull it poleward. I'll skip that. Okay, so what's going on there? It's clearly opposite to our prediction, so something must have been wrong with the budget that I initially wrote down. So here's the full budget, this full PV variance budget. Before I set this higher order term, in this case I've actually explicitly written down what this higher order term looks like. You could call this an Enstrophy flux or a PV variance flux term. So this is also included. So if the prediction from the small amplitude budget is wrong, then we should check whether that higher order contribution does anything. So that's what I'm going to do here. So now you have these three terms, and this is how that looks like in potential temperature coordinates. So what is the importance of those higher order terms, those third order correlation terms? So here's the line plot similar to what I shown before. This is the variance tendency coming from the PV fluxes. So this is this production term with the upgradient fluxes here just poleward of the subtropical jet. And the blue line shows the tendency coming from these PV variance fluxes, in fact, the convergence of those fluxes. And the striking thing is that they match each other very closely. I was actually, when I first got this, I was very stunned because I'm working with a reanalysis product, which means that it's a model married to observations, and you're trying to constantly pull the model toward the real world state. And usually what that means is you mess up the system a little bit. And if you look at these higher order budgets, I was not expecting this to close very well. And so when I was initially plotting, and given that these are highly derived fields, I got a triple correlation. PV is a complicated term to calculate. I was kind of stunned that they match so well, but they do. And what this shows you is that the balance is between this production term of the PV fluxes and the Enstrophy flux convergence. So what does that mean? That means that in this region of the atmosphere, finite amplitude effects are crucial. They're first order. You can't just sort of bring them in at second order to modify your initial result and make it improve it. They're at first order importance. In fact, what we thought was going to be the dominant balance with the dissipation term seems to be of much less importance here, because I'm already fairly close.
Why did you think it will be third order to begin with?
The term is third order, just in terms of the order of the terms. And this is coming all from linear thinking, right? So you come from a wave solution thinking where you have linear waves, the amplitudes are small, so anything higher order will drop out. So that's where that thinking comes from. It's true, if you come from the more turbulence-like thinking, then you ad hoc, you already know that the higher order terms are going to be important. But most of the theory, at least in this field here, comes from sort of linear wave-like, wave dynamics thinking. Okay? So what does this mean? We have these finite amplitude effects. What that also means, if you look at this triple correlation term there, it means that you have to have interactions across the wave spectrum. If I put the same wave number into these perturbations there, I'm not going to get any correlation, because the average of sine cubed is 0, or the average of cosine cubed is 0. I need two different wave numbers to couple in order to get something there. So just the fact that this term is so important already tells me that there needs to be interaction across the wave spectrum. And so this is just proving that that's really the case. This is the same picture as before with the upgradient, downgradient PV fluxes, but broken up into wave number 1 and 2 in the top, and wave numbers 4 to 7 in the bottom. So if you remember in my animation, I said the dominant activity comes from these waves 5 and 6 or so, right? That's what we could mostly see. That's all going on down here in this plot, waves 4 to 7. And everything is downgradient there. This is where all the action with the wave breaking and so on takes place. The positive, the upgradient PV fluxes, they come from the planetary scales, wave 1 and 2. So wavelengths of 20,000 kilometers, really, really long waves. That's where all these upgradient fluxes come from. And here's just another way to look at that. At 350 Kelvin, we have the black line is the result from before. The red one is wave 1 and 2. Blue is 3 to 7 in this case. And you see that this is all negative and this is all positive. What you can also see a little bit here is that the peak in the negative, in the downgradient fluxes, is slightly equatorward from the peak in the upgradient fluxes. And that's something that I'll come back to in a moment. Okay. So what I'm going to do next is, this was all climatology. I'm not going to move into sort of an eddy life cycle. I'm going to try to analyze what's really happening as I have amplification of Rossby waves along the tropopause and breaking and what's sort of subsequently happening. So I'm going to look at this sort of eddy life cycle. And what I'm going to use from my eddy life cycle is the Enstrophy, because that's what I cast my budget in, PV variance. So what I've done is I picked the latitude on 350 Kelvin, 200 hectopascals. I picked the latitude where I have the peak in my upgradient PV fluxes. And I take the PV variance at that latitude over northern winter. And then I regress the field over time and latitude onto that index there. And so the first thing is just the Enstrophy regressed onto itself. And you see that it amplifies and then it decays, so that's expected. The time scale is about a week or so, typical synoptic time scale. You can also see that it's slightly moving forward as it does so. And in order to really emphasize that, here is the zonal mean zonal wind regress on this PV variance with red positive and blue negative, and you see that there's a very clear poleward shift of the zonal jet going on, okay? A dipole of positive and negative indicating that there's a shift. So while all this happens here, while all this action takes place, my jet is moving forward, okay? So this is the same thing as before zoomed in. Here is the production term in the life cycle, the PV flux contribution. And what I see is that it's down gradient negative before I maximize, and then it's up gradient. This is just what I expected from my schematic that I showed before. As you have amplifying waves, you have down gradient fluxes. As they decay, you have up gradient fluxes. And down here, it really looks like a lot of this is compensating, right? You have down gradient before, up gradient afterwards. If you integrate over time, not a whole lot is going to be left. A little bit is going to be left. But what also happens, is the up gradient flux part, because everything is moving forward as I do this, the up gradient flux part is shifted forward relative to the down gradient flux part. So that if I integrate over time here, there's a latitude range right there in this neighborhood where the up gradient fluxes are going to remain if I take a time average. And the reason that they remain there is because I have a poleward shift of the jet while all of this happens. And to really sort of show that at the same time that this is moving poleward, I have an Enstrophy flux poleward. This is the green dashed lines there in the background. So I'm generating Enstrophy here with the down gradient fluxes, okay? Then I'm fluxing the Enstrophy poleward. This is the green lines. And then I have wave decay with up gradient fluxes afterwards that happen poleward from where the down gradient fluxes happened. So if I look at that, okay, that seems to explain that after the life cycle I have this up gradient flux remaining. How does this fit into the interactions across the wave spectrum that I've discussed before? So if we break up the PV flux contribution into the wave numbers again, the left has waves 3 to 7, and the right has waves 1 and 2. We see that all the down gradient fluxes before in the amplifying stage come from the medium scale waves that we could see in the animation amplifying and breaking. And all the up gradient fluxes come from wave 1 and 2. Okay, so while these waves here break and flux Enstrophy, the Enstrophy goes into waves 1 and 2, where you have wave decay and where you eventually get your up gradient fluxes from. So it's really this coupling from the higher wave numbers upscale into the lower wave numbers that's crucial here, coupled to the shift in the jet poleward while everything happens, that gives you the up gradient fluxes in the end. Okay, so how should I imagine this to happen? So what I've done here is I show this life cycle. It's going to flip through time as a function of longitude and latitude in this case. So this is similar to the animation I showed. This black dashed line shows the location of the tropopause, the subtropical jet. Here's the Pacific jet stream. Here's the Atlantic jet stream. And then what I've regressed in this case is just PV anomalies. Okay? And you're going to see they're always blue. They're always negative. And this is at lag of minus 10 days. So this is quite a bit before the maximum action takes place. So as I flip through this, what you see is, well, first of all, most of the action is in the Pacific jet right there, which is the strongest jet in the northern hemisphere in wintertime. But what I see is I have an anomaly coming in on the left there at the jet entrance. It's amplifying, and it's going over to the exit over here, where now I have maximum anomaly, and then this is going to decay. But what you also see is that the anomalies are really my medium scale wave. If I look at this anomaly, and this is going to correspond to this wave 5 or 6 sort of wave number. So this is clearly the action is driven by those medium scale waves, and I get these strong PV anomalies signifying that there's these waves going through, and then it goes out on the other side and it decays. But what was crucially happening, which is kind of hard to see, what's crucially happening, while all of this happened, the climatological pattern, which has a wave 2 in it from the 2 localized jets, got amplified. The gray line shows my climatology, and the black line is at lag 0. So this is when most of the action happens. And I see in the black line that the amplitude of that wave 2 in the climatology is amplified with respect to the climatology. So if I flip through this again, this is going back, sorry, and then now through it again forward, you can actually see how, if you focus on the black dashed line, how it's amplified at lag 0. And I think that's how that interaction really happens, is you get this wave amplification at the exit region of the Pacific jet there, and it amplifies the background wave 1 and 2 signal from the climatology. Okay. So, to conclude, you would usually expect downgrading eddy PV fluxes from a basic analysis, small amplitude analysis. But when you analyze the real data, you find that there's an upgradient flux region close to the subtropical jet. And it's at first, it was very surprising because it exists in a region of very strong positive PV gradient. We found that everything is basically driven by finding amplitude effects, which, if you look at the animation, is not very surprising. Everything looks very fine at amplitude in the animation. You know, there's no small amplitude waves going along the tropopause. Everything is wide in latitude. And we found that you need these Enstrophy fluxes to explain this. And it's the decay stage of the waves that gives you these upgradient fluxes. And that really you have an interaction or an upscale cascade, if you want, from the medium scale waves up to the planetary scale waves. What is also important is that while all of this happens, while this wave breaking happens along the tropopause, you had a shift in the jet poleward, and that was also crucial to explain what was going on. And the final point, I'll just quickly go back here, sorry. If I take this entire region here, where all the wave activity happens, and I average across this entire region in latitude, what I'm doing in that case is I'm taking into account that there's a poleward jet shift. And if I do that, you can actually visually see that then the blue and the red are really going to cancel each other. And in that case, I'm back to my downgradient eddy PV fluxes. And so, in a way, you could sort of rescue the old paradigm in saying that, okay, what you also need to do is you need to average in space over the eddying region, and only then do you recover that downgradient flux paradigm. If you do it locally, you get upgradient fluxes. Okay. I think that was my final conclusion. Thank you.